Hi folks, and thank you very much for joining the QBCC Tradie Tour Concreting webinar. My name is Harm Tukuru and I will be your MC today. I'm the Education and Events Coordinator for the QBCC Education and Engagement team. Before we begin, I would like to acknowledge the traditional custodians of the land that I'm speaking to you from and pay my respects to the elders past, present and emerging. I also acknowledge the traditional custodians of the land on which each of you are living and working, and I extend that respect to Aboriginal and Torres Strait Islander peoples here today. Okay, moving on just to a little housekeeping. In regards to the survey you'll receive, so you'll receive a survey at the end of the webinar. The survey is asking for your feedback. It only takes a couple of minutes to complete, and it really helps us plan for events that are relevant to you. In terms of audio settings, if you can't hear the sound, make sure that you check your device settings. For Android users particularly, use the volume buttons as normal, but this time adjust the media channel volume. For questions, please send through questions via the chat box on the right-hand side of your screen, and you can ask questions as soon as you think of them via that webinar chat box. And lastly, just as a reminder, the QBCC does not endorse one brand of product over another, and written or visual references to branded products are used for illustrative purposes only. Okay, with that all said and done, I would like to introduce our presenter for today. Joining us today and representing the CCAA, Cement Concrete Aggregates Australia, we welcome Mr. Michael Booy. Mike has worked for the last 8 years as the Regional Technical Manager for Hanson Construction Materials, covering Queensland and the Northern Territory as well. He has worked in manufacturing, project management and consulting roles in industries including steel, fibre, cement and concrete in New Zealand, Australia and Southeast Asia as well. Mike, if you're there, I'd just like to invite you to turn the camera on and your microphone on, and I'll pass the presentation over to you.
All right, thanks, Harm. So I'd just like to start out by saying I'm very pleased to do the presentation today. My boss is more than happy for me to spend the time on this because we put over 1 million cubic meters of concrete into the Queensland market, and if there's any problems with any of that concrete, that comes to me and my team. So I wouldn't say that we've seen everything that can go wrong, but we've certainly seen a lot. And if we can improve the practices of even a few people out there, then this is a worthwhile exercise. So some of the things we'll be talking about tonight are materials and properties, specifications, planning, finishing. We'll spend a bit of time focusing on residential driveways and paths, as well as giving you some quite good reference material on Australian building codes, standards and CCAA publications. We'll move through the slides pretty quickly, so we've got time for some Q&A at the end as well. So just talking about materials and properties, for everything to come together well and produce a product that the customer is happy with, we need to get all of these things right. So there's materials, there's the concrete, the construction and the design. So the materials, I think people are aware that covers aggregates, cement, and when I say cement, I'm talking generally about cementitious products. So that covers things like GP cement, fly ash, and ground blast furnace slag. Obviously, water and admixtures also go into making up the concrete. So it's my team that looks after the mix design of the aggregates, cement, water, and admixtures. And once we design that, it all gets mixed at the concrete plant and gets delivered in the concrete agitator truck. And then it's up to the concrete placers to place it and do all the right things in planning, including compacting and curing, which we will talk about during the presentation. But the design is a very important part of it as well. So just to give an example. We supplied concrete to a walling system down the Gold Coast, and that walling system was made of a concrete fibre product, a fibre board with gussets joining the two boards. And the idea is you pour the concrete, and then that becomes the finished product, and you can paint the fibre board, and that was done, and people moved into the apartments. But what happened was that when the light was coming through a certain way, you could see very fine cracks. So we had to engage an engineer to help us figure out why this happened. And it really came down to two things. The customer had ordered a block fill product for filling the walling formwork, which was, as I said, a permanent formwork. And although the block fill product is great for filling blocks, it's a fairly sandy wet mix, and therefore has a fairly high shrinkage. And that high shrinkage, together with the second factor where they didn't quite follow the manufacturer's recommendations for the reinforcing, led to these fine cracks that propagated through the permanent formwork. So that was quite a costly exercise. The builder had to resheet those walls, which were supposed to be the finished product. So as you can see, that engineering design and architectural design, and also we'll talk about other factors around environmental conditions. It all plays a role in the performance of the finished product. So this is just an example of concrete that's come out looking very, very well. It's a nice bridge there. Here's some really nice off-form finished concrete, very monolithic in its look. And this looks like concrete that's been used with off-white or white cement to give a nice light finish. So concrete, as you know, is made up of the raw materials that we spoke about earlier, and it exists in plastic and hardened state. So there's this dormant period, which is generally during the batching and delivery period, and then there's a setting period where it goes through an initial and then a final set, and then finally after that 5 to 6 hours or so, it goes through a hardening period where it gradually gains its final strength. So typically concrete will get about 60 or 65% of its 28-day strength in 7 days. And once it gets the 28-day strength properties, it'll get a little bit more, up to 56 and 90 days, but generally only 1 to 3 or 4 MPa. So you can count on about 60-65% in 7 days, and then the majority of the strength at 28. So when we order concrete, one of the most important things is the workability of the concrete, and the workability needs to be specified in a way that's suitable for the placement method. And typically when we talk about workability, we're talking about slump. So you can see this little picture on the left. The slump test is, as I said, a measure of workability, and what you do is you fill the slump cone with concrete in layers while you rod it to compact it, and then you lift that cone up slowly, and the slump measurement is the amount that it drops from what was the top of the cone down to the top of the puddle. So this is fairly high slump concrete. This is 180 millimeters. If you look over on the right here, this is 80 millimeter slump. So this is much more typical of what might be used for housing slabs or driveways. Although the concrete standard AS 1379 does say that if no slump is specified, then the default is 100. I think it's recognized that most places prefer 100 millimeter slump, and there's a benefit in doing that because you avoid the temptation for the places to add excess water. So you'll hear me talk quite a lot during this presentation about uncontrolled water additions. And basically it's a bad thing, and that's if you take one thing away from this presentation, I want you to take away that uncontrolled water additions are a bad thing. And we'll go through some of the reasons why throughout some of the other slides. The one exception to that is related to this slump here, which looks like zero slump. So when we supply material for curbing, we're required to supply it on the dry side for the contractor to make up to their required consistency. More often than not, they don't like to add water, which is, as I said, the exception, because it stands up from their slump machines, from their curving machines rather, and they can get a nice quick production rate. The only problem with that is that we supply curb typically to a minimum cementitious content of 280 or 320 kilos. When concrete goes hard, it's not drying, it's actually hydrating. So it's a chemical reaction that occurs between the cementitious products and the water. So if there's not enough water added, then the cement doesn't have enough to react with, and it doesn't get that strength, and it doesn't get the compaction. So we had a case supplying curb mix to a subdivision. Part of the curbing was impacted by a grader and broke, and someone walked around with a bit of 2x4, hitting the curb and demonstrating that it didn't have the strength that it should have. And ever since that time, we've just refused to supply curb concrete to a strength guarantee, because it's not so much under the control of the concrete supplier, it's largely under the control of the curbing contractors. So that's the only exception of uncontrolled added water being a bad thing. So we'll go to the next slide, and this has got some graphs in it that helps explain why uncontrolled water additions are bad. So this top graph on the right, this has got compressive strength on the vertical axis, and it's got water cement ratio on the horizontal axis. So the water cement ratio is simply the water in kilograms or liters divided by the kilograms of cementitious material. So you can see when we've got a water cement ratio of 0.8, and you go up to the 28-day line, because concrete strength when it's ordered is referring to the 28-day strength. That suggests that we will get a 28-day strength between 15 and 20 MPa, but of course it depends on the raw materials, so it will vary a little bit from place to place. As the water cement ratio decreases, and typically what we do when we're making the concrete is the water doesn't change too much, but we add extra cementitious material. So by the time we get that much cement in there, that there's a water cement ratio of 0.4, we're achieving 50 MPa concrete. And if we take it all the way down to 0.28 or 0.3, we're getting close to the 80 or 100 MPa. So you can see that as you add water, you're dropping the strength of the concrete. Now this graph below, this is looking at the coefficient of permeability. And what it shows is that as we increase our water cement ratio, our permeability increases gradually at first, but then very rapidly. So you can see in particular for low strength concrete, such as 20 or 25 MPa concrete, as we add more water, our permeability is increasing exponentially. And we'll talk about this a bit later as well, but you can imagine if concrete's got about 200 litres of water in it per cubic metre, we only need about 60 litres of that to react with the cementitious product. The rest of the water is just there to make it workable. So as that water evaporates, as the concrete dries, if it's in a dry environment, then where the space where that extra water was, it just leaves porosity. If the concrete is more porous, it's easier for water and chlorides to absorb and travel through that concrete. And once that chloride front reaches the steel reinforcing, that promotes corrosion of the reinforcing, and the corroded steel takes up more space than non-corroded steel, so that tends to spool the concrete off, and that causes what you might have heard as being concrete cancer. It's been on the news a fair bit, those older apartments on the Gold Coast where you've had concrete spooling away and corroded reinforcing is visible. That's a much greater risk where you've got porous concrete. And by porous, I mean concrete which is lower strength, and particularly concrete where there's been extra added water. This little graph here on the left, that just talks about the type of cement. So I mentioned at the start of the presentation that when I talk about cement, I'm using it as an inclusive term that includes supplementary cementitious materials, or SCMs, such as fly ash and slag. So when you mix GP with these SCMs, you have what's referred to as a GB cement, which gives less strength gain early on, but a longer strength gain later. And it's worth pointing out that the use of those SCMs is very important as a durability enhancer. And in fact, Queensland Main Roads insist that we use a certain amount of fly ash in concrete, because they recognise that fly ash not only helps the workability of the concrete, but it also assists in improving the durability. So we'll talk a bit about specification, ordering, and delivery. The standard we use as a concrete supplier is AS 1379, and that covers all of the things on this slide. And we'll look at the next slide and just talk a little bit about what the difference is between normal class concrete and special class concrete, and the sorts of things that we need to know as a concrete supplier. So normal class concrete is generally covered by these grades, so either 20, 25, 32, 40, or 50 MPa. And the other things we need to know are the slump, or the workability, and as I said, that should be related to your placement method. It generally won't impact the strength, so there shouldn't really be any need for the engineers or specifiers to specify the slump. Normally, from an engineering perspective, the strength is required, and I think the slump or workability is more related to the placement method. So the maximum nominal aggregate size, typically in Brisbane or Queensland, in fact, it's either 10 or 20 millimeters. Certainly down in Melbourne, they sometimes use a 14 millimeter. Method of placement can be shoot, pump, spray, tremie. The rate of placement we need to know, so we know how many trucks per hour to send. Whether or not you want the testing is also important, and you don't really need to talk about air entrainment. We can add a little bit of air into generally into lower strength concrete just to aid the finishability, but we don't normally add it for any other reason. Certainly in places with very cold climates, then air is added for reasons of protection against freeze thaw. So if you're talking about anything apart from that, such as higher strengths like 65, 80, or 100 MPa concrete, or spread concrete, so spread's a workability measure as well. So typically we order concrete by slump, but we can now make concretes that are self-leveling or super workable, and rather than measuring the collapse height from a slump cone, we measure the diameter of the puddle. So that's a feature of special class concrete, and also things like shrinkage requirements or flex strengths. We'll go to the next slide, and that looks at delivery. So these are some of the things we need to control as part of the delivery of the concrete. We have to make sure we control against segregation and loss of workability. We have to make sure that the concrete's within that temperature range of 5 and 35 degrees. We need to discharge within 90 minutes of mixing. And then there's normally a delivery docket. Sometimes that's paper, or more often than not, it's a paper docket, but some of the concrete companies are now working towards electronic dockets or paperless deliveries. And the method of transport, I'm sure you're all familiar with the concrete agitator truck. Now, when I say that uncontrolled water is a bad thing, I should say that under 1379, you are able to add water as long as the slump is below the required slump tolerance, and it's been no more than 75 minutes since batching, and that you mix it thoroughly after the added water. And I should just say too, if you order 80mm slump, but the places like it at 120, you're much better off to order it at 120 slump. If we add water to increase the workability, we'll also add cementitious to make sure that all of the strength and durability properties are maintained, which is not what happens when uncontrolled water additions are done on site. So this is just, this is the list of things that are impacted by uncontrolled water additions on site. So obviously the slump is increased and the workability is increased. And normally that is the point when people ask for extra water additions on site. But we need to understand that it has a detrimental effect on all of these other properties. So compressive strength will be decreased, the rate of shrinkage cracking will be increased, the risk of surface dusting is increased, the risk of segregation is increased, the volume of bleed water is increased, the benefit of compaction is decreased, the benefit of curing is decreased, durability is decreased, and the permeability, as we've discussed already, is increased. So lots of things are going to happen that are detrimental from those uncontrolled water additions. And certainly we instruct our drivers, if the customer requests or insists on additional water being added, that they are to make a note of that, and we will not guarantee strength and performance if that happens. And there's a little diagram there just showing what happens to the strength as the water is added and the slump is increased. So we'll talk a bit about planning, site preparation, placement, and compaction. And this next picture is a waffle slab. So when you're planning for this work, you need to obviously do the site preparation, make sure you've got the right soil conditions there for the design of the slab. You need to think about site access. Have you got enough people to place it at the rate that you've required or requested? What is the concrete specification? How are you going to place it? How are you going to compact it? And certainly with these waffle slabs, it's probably a good idea to compact down between the polystyrene blocks so you don't get differential settlement. And we'll talk about compaction and then planning on the finishing, jointing and curing as well. And we'll particularly talk about the curing in the next few slides too. So these are some of the things that need to be covered during site preparation. So the site investigation, the soil conditions, soil types, excavation and fill, subgrade, subbase, vapor barrier or damp-proof membrane, formwork installation, steelwork, set cover depths. Remember we spoke about permeability of concrete and the chloride front that does gradually work from the surface of the concrete through the concrete towards the steel. That's why we have a particular cover of steel. We need to make sure there's a minimum cover of concrete, so it takes a particular length of time before the chlorides get in and attack that steel. And we need to make sure that the forms have release agent applied. We don't want to go whacking the forms with a hammer and potentially damaging the slab in doing so. So placement can be placed from a chute. So there's a chute in place there in the picture. It doesn't look like the concrete agitator chute. It looks like something that's been jury-rigged. Can be direct from the truck. It can be done through a bucket or a kibble. Can be done and is done probably most commonly through a pump, but it can also be done if it's shotcrete by spraying. So a fundamental consideration is to avoid segregation, and we'll just talk a little bit about placement rules. So there's a few rules there, and it's probably best demonstrated through some of the pictures. So generally when you're placing, you want to place onto the concrete that's already been placed, so that gets a nice a good bond and does a little bit of compaction for you. The incorrect method is shown pouring away from that existing face. So pouring on a slope, you'll see that this is starting at the bottom and they're working their way up, and you've got a baffle so that the concrete doesn't fly out at 100 miles an hour. And this is the incorrect method. They're doing it correctly in terms of starting from the bottom, but they're letting it free fall, which is just going to cause the potential for the aggregate to separate. Down here, we've got a drop chute, and the drop chute is pretty close to the existing concrete. So that's preventing this greater than 2 meter free fall that you see on this next picture. So if you let concrete fall for greater than 2 meters, it'll have the risk of causing the concrete to segregate, depending on the nature of the concrete and what the slump or the spread value is. There's another set of pictures. These ones just show concrete being done in a logical placement method, so starting in one corner and working your way in a logical manner rather than going piecemeal. These bottom pictures just show that correct placement method of starting at the bottom and working towards the top. When you work from the top and you screed it, you can kind of get tearing and rolling that might not give the surface finish that you're after. Now, just remember that these are best practices, so you know, I'm sure there's times when these aren't followed and you can still get a reasonable finish, but these are just the best practices that are recommended. So this page shows piling or columns, and again, it's just demonstrating the use of this funnel or tremie to make sure that the concrete is not free falling any distance. And certainly if you're doing a pile and you're placing concrete underneath water or underneath drilling mud, for example, then that tremie would have to go underneath the surface of the concrete that's already been placed. So as the concrete rises, it's got a nice clean profile and displaces any water or drilling mud up above it. And you can see the incorrect method on the far right here, where it's just free falling and potentially leaving, as in this picture, spaces where the concrete just hasn't flowed out and completely filled the form. So compaction. So you can carry out compaction with pokers or internal vibrators or surface vibrators such as vibrating beams or screeds or form vibrators. And we'll talk about why compaction is important. And just point out, I guess, on fairly thin slabs like pathways or driveways, you get a certain amount of compaction with the shovel and by walking around with your boots. But if you do use a poker vibrator, they're made to be used vertically. If you use them horizontally to drag the concrete around, particularly if you're doing decorative concrete driveways with exposed aggregate, you might end up segregating the paste and the stone, and the finished product will look a little patchy in terms of patches of a high concentration of aggregate and patches with a high concentration of paste. So we need to be a little bit careful about not using poker vibrators horizontally as an aid to moving the concrete around. So look at this graph here on the right. So this shows the amount of air voids on the horizontal axis and relative strength on the vertical axis. So I guess if we order 25 MPa concrete, 100% would be your 25 MPa. And as the percentage drops, so does the final strength of the product. So when the concrete comes out of the concrete agitator, it can easily have as much as 10 or 12% air. If we vibrate that concrete properly, we should get that down to 1 or 2%. But if we don't compact, if we don't vibrate, and we have the air sitting at 10 or 12%, look what happens to the strength. It's only sitting at sort of 40 or 50%. So if I order 25 MPa concrete, I don't do any compaction, there's a good chance I'm only going to end up with 12, 13, 14 MPa concrete on the ground. So the compaction of the concrete will increase the strength and other properties. It will decrease the permeability. You just think if all those air bubbles are forced out of the concrete, then it's less permeable concrete and it's less likely to carry through water and salts and cause efflorescence and all those other sorts of problems. It permits the use of lower slump concrete because it does liquefy the concrete when you vibrate it. It will also reduce settlement and plastic cracking, and we'll talk a little bit about settlement and plastic cracking in the slides ahead. It improves the concrete steel bond and improves the surface finish. But we do need to be a little bit careful that we don't over vibrate and cause segregation of the concrete. Okay, so this is the compaction process. So you put the vibrating probe in, and there's stage one, a few seconds just to liquefy the concrete, and then stage two, you'll see the bubbles coming out, and most of that entrapped air should be gone within 7 to 15 seconds. But you'll see that the pokers are inverted, are inserted vertically. They're not used in a horizontal fashion. So this slide talks about the evils of added water, which I've already covered a fair bit. And the diagram, you can see this is an elevation view and this is a plan view. So this shows cracks appearing over the steel reinforcing. So this is settlement cracking. So what happens when concrete bleeds is that the water rises and the stone settles down a little bit. If the stone can't settle down past the steel reinforcing, then the crack will open up. So again, compaction or vibration will remove the air and reduce the amount of settlement. So it'll reduce the risk of settlement cracking. Not adding excess water will also reduce the risk of settlement cracking, because if the water's not bleeding up, then the stone isn't settling down as much. And if you're quick enough, if you see this happen, and if you're quick enough, you can re-vibrate and close the cracks. But that's settlement cracking. So we'll talk a bit about finishing, jointing, and curing. So the purpose of finishing is to achieve a level, flat surface with the required density and texture. So finishing is carried out prior to the final set of the concrete. If the concrete had already final set, then you wouldn't be able to level it. You would have missed the window. And finishing involves screeding, normally bull floating, troweling, or helicopters or ride-ons. There's a note here about bleeding. Bleeding may occur after screeding and initial floating, and we've got to delay the troweling until that water is evaporated. And there's a great little diagram that shows hitting the gap. So this is hitting the gap here. So you've got finishing operations at the top. We're all familiar with the placing, screeding, and bull floating. And then it talks about weighting. So the reason we're waiting is we're waiting for the concrete to gain some strength, but we're also waiting for this bleed water sheen to evaporate. What happens if we finish prematurely and we work this bleed water sheen into the concrete? Remember when we spoke about water cement ratio? If we add more water to the concrete, the water cement ratio increases and the strength decreases. If we work this bleed water sheen into the concrete, or if it rains and we work rainwater into the concrete, we're going to get a very weak surface on the concrete, and that'll show up as a dusty surface. So we want to wait for that bleed water sheen to evaporate and for the concrete to stiffen. And when a boot print is no more than 6 millimeters, we can get on with a power float. And when it's no more than 3 millimeters, we can get on with a ride-on float. And that's hitting the gap. So we're getting on there while it's still soft enough to level, but after that bleed water has evaporated. And it's really important that we do that surface finishing, because it's that surface densification that provides that surface abrasion resistance. I've seen car parks where on the corners on the ramps, where the steering tires are screwing around on the concrete, that look like exposed aggregate driveways, because all of the paste has been screwed off from the top of that concrete. So if we avoid the bad things, like we make sure we compact, we make sure we cure, and we're going to talk about curing in a little while, and we make sure we densify that surface, then we'll avoid that sort of thing happening. So this is a nice little diagram. So there's a slide on jointing. So we all know that concrete shrinks, right? And when it shrinks, if there's any restraint, it'll crack. And restraint can come about from a number of things. It can come about from friction with the ground. It can come about by being locked in with beams or foundational design. So generally, we need to make sure we design control joints that will cause cracks to initiate in that location. So it's still going to crack. It's just that people won't see a jagged crack, they'll see a nice clean joint. And you'll see that in this diagram, the reinforcing's not going through that joint, but there are a few other ways of doing that, and they're shown on some of the subsequent slides. And these are just, this is some information on control joint spacing. A note here that it should be to a depth of at least 1/4 of the concrete to ensure that that's where the crack does initiate. And then the weakness planes, as they're called, can be done by scoring or grooving the plastic concrete, inserting a crack-inducing device, and sawing the concrete. When it comes to sawing the concrete, you kind of need to get on it pretty quick. So ideally the same day, or as early as possible the next day. You've probably got a bit more time in the winter than you might have in the summer. But if you don't get in there early enough with the saw cuts, you might find that the cracks have appeared where they want to. Okay, so we're going to talk now about curing. So you've heard me talk about the evils of water, but water is also very important for concrete. It's just that we need to make sure it's the right amount of water. It's the amount of water that was intended when that concrete was designed. So remember I said concrete doesn't go hard through drying, it goes hard through hydrating. So it's a chemical reaction. You're getting water reacting chemically with the cementitious products. So concrete needs water to attain its design strength. And curing, all curing is it's just about holding the water into the concrete. We don't want it to evaporate. So this top diagram shows, in a similar way to what that compaction diagram did, it's got the relative strength on the vertical axis. So again, if we've ordered 25 MPa concrete, 100% would be achieving that 25 MPa strength. And it's got different curing regimes on the horizontal axis, going from the best possible, where it's continuously cured in a moist environment, to the worst, where it's just been left to cure in the air. And you can see that when it's left to be cured in the air, so in this situation, you know, we've placed the concrete, we've finished it, and we just walk away, we're only achieving 40% of the strength that we should be achieving. If we cure it for 3 days, we're achieving over 60% of that strength. And if we cure it for 7 days, then over 70% of the strength. So you can see that curing process, that process of holding water into the concrete so the concrete can properly hydrate and gain strength is pretty important. And it also has an impact on the permeability of the concrete. So if we cure it, and in this diagram, we're talking about coefficient of permeability, so a higher number is better. Your coefficient of permeability rises pretty quickly up to that 3 to 7 day, and then it still rises, but at a lesser rate past the 28 and further. So you can see it's really important to try and cure for at least that 3, 4, 5 days, up to 7 days if you can, to get that strength requirement, and also to get concrete that's not too porous and is therefore more durable. So these are some of the things that you get: increased strength, more resistance to abrasive wear, less permeable, less susceptible to damage, and reduced early age shrinkage. So these are just some methods of curing. So this is this picture on the left is a spray-on curing compound that just holds that moisture into the concrete, stops it evaporating. Excuse me. And on the right, there's an impermeable layer that just holds the moisture in the concrete. So you can even use plastic. I did my carport a few months ago, and I just put plastic down and made sure it was wet underneath the plastic, but it'll stay wet anyway as long as you've got it nice and tightly formed around that concrete. You can also use a water dam, like use sand or some other material to make a dam and just fill it with water. So it's all different methods of curing, and all you're trying to do is hold that water in the concrete while it hydrates. So we'll get on to residential driveways and paths. And you can see here there's some nice joints. You've got a saw cut joint here, got another saw cut joint here. But it looks like quite a long distance between these two saw cut joints. So the concrete's shrunk and it's here. Well, I'm going to just crack here. So it looks like that's a dry and shrinkage crack, and that's probably occurred because the joint spacing's too big. So there's quite a few different types of cracks. So I've talked about plastic settlement cracking, which follows the pattern of the reinforcing steel. We've talked a bit about plastic dry and shrinkage, but we're going to cover that a little bit more. We've talked about dry and shrinkage, and this is an example of dry and shrinkage just here, due to the concrete shrinking as it dries over a period of 6 to 8 weeks. And you can also get cracking through ground movement, overloading, or just poor joint detailing. So we'll just look at the next slide, and that just gives you some reference material on some of the documentation, some of the Australian standards that you can look at in terms of how you control joints and what's considered a defect and what's not. Generally, if it's a millimetre or less, it's not considered to be defective. This just talks about the different strengths you should order for different situations. N20 for pedestrians, N25 for pedestrians and light vehicles, and N32 for pedestrians and commercial vehicles. So higher concrete strength may be required, not just for structural reasons, sometimes for abrasion resistance, sometimes for durability reasons, so you've got better resistance to salt penetration. Higher strength concrete will also reduce the risk of concrete cracking. And just a little note here, if you're dealing with coloured or decorative aggregates, then that's considered special class concrete. There's a slide here on site preparation, and this is a good example of a crack that's most likely due to some ground settlement. So if the ground can't provide that even support for the concrete, then the concrete's going to crack. And there's just some notes on what you need to do that correct preparation. And a few diagrams on this side that just show subgrade, sub-base, and then a layer of sand or polyethylene. The polyethylene's quite good because it does reduce the friction between the concrete and the ground. So if the concrete can shrink in on itself, it won't crack as much. And also the polythene keeps the water in the concrete and directs the water up as bleed water, which is a good thing. You don't want the water all sucked into the dry ground. So if you don't use polythene, it's probably a good idea just to wet that ground down prior to the concrete going in, just to make sure that that ground doesn't take the water out of the concrete. And this is another way, another method of doing that control joint. So this one uses a proprietary pressed metal key joint. You can see that the reinforcing doesn't travel through the joint, but because of the shape of that joint, you'll avoid differential vertical movement either side of that joint. Talks also about using bar chairs at maximum 600mm centers. Steel reinforcing should be in the top half of the pavement with at least 30mm cover to the surface and 40mm cover to the slab edge. And we know why that's for, right? We don't want that steel too close to the surface where it's going to be attacked quickly by that moisture and chlorides. And it does say steel reinforcement shall not be continuous, but there's another diagram further on that shows where it is continuous, but it's done in a way that it's not fixed into one end. So placement and compaction we've talked about. So we need to be careful to avoid segregation. Make sure we get adequate compaction so we don't have that air bubble causing low strength and porosity and durability issues. Surface vibration can be done, or we can use poker vibrators. And generally the small or large diameter depending on the thickness of the section. Okay, plastic shrinkage cracking. This is pretty common. You can see by the picture that this cracking pattern is fairly random. So what is plastic surface cracking? Just picture a dry lake bed. You've probably all seen photos of a dry lake bed which is just all cracked. So that happens when the top of that lake bed dries out and shrinks while it's still muddy underneath. So that's the same mechanism for plastic shrinkage cracking in concrete. We're getting drying of the surface while the concrete is still plastic underneath. So that surface layer is drying and shrinking. And if it's not drying and shrinking underneath, then you're going to get cracking on the surface. So that's plastic cracking. So to avoid it, we need to make sure that while that concrete is setting, the top remains wet. And that's why bleed water is a good thing. So the bleed water rising up keeps that surface wet, prevents it from drying out, allows it to set with the water and gain some strength. So there's times where plastic cracking is a higher risk, and that's hot, dry, and windy conditions. And there's a little diagram here that allows you to work out what the evaporation rate is going to be depending on the relative humidity, the concrete temperature, and the wind speed. Or you can just use the CCAA app that'll look at the weather conditions and tell you. And if you get evaporation rates up around 0.8 or 0.9 kilograms per square meter per hour, it's high risk. It's high risk of plastic cracking. You might need to do things like put up windbreaks, try and do the walls first if it's a commercial building, or use aliphatic alcohol. So aliphatic alcohol is, or anti-VAP, is a substance that you spray on as a fine mist once you've screeded and bull floated the concrete, and it helps prevent evaporation of that bleed water. So you don't need to use it all the time. You just need to use it when there's a risk of high evaporation and the surface drying out. If you do use it, you need to use it as a fine mist, and you need to reapply it every time you undertake a finishing operation on that concrete. Let's go to the next slide. So this is a picture of the app that's available through CCAA. So that'll go and look at the weather conditions and tell you what the evaporation rate of the concrete is going to be, of the bleed water from the concrete. So you can also reduce the risk of plastic cracking by all of these things. So having a higher bleed, using SCMs like slag and fly ash, use of chemical admixtures, plastic fibers. So plastic fibers, particularly the microfibers, they just act to help prevent plastic cracking. Dampen the subgrade. Remember, we spoke about dampening the subgrade, particularly if you're not using plastic, so the water doesn't get sucked down into the ground. You want the water to go up as bleed water to the surface of the concrete. Change the placement time. So it's not uncommon in the summer for us to be delivering concrete at 3 or 4 in the morning, so we avoid the risks of plastic shrinkage cracking. Cooling the concrete. Sometimes we'll cool it with chilled water or ice. So that'll give you longer placement times, better slump retention, and less risk of plastic shrinkage cracking. Shading the surface, erection of windbreaks, and as I said, the use of an evaporative retarder. So finishing. Finishing is very important, as I said earlier, for densifying that surface, giving it some resistance to wear and dusting. This looks like a broom finish. But if you're going to do a broom finish, you still need to make sure you densify that surface and get some strength there before you apply that broom finish with a stiff broom. So it just talks about compaction or densification of the concrete surface by troweling. the appropriate finishing operations such as brooming or wooden or sponge float finish to avoid a slippery finish. And then the broomed finish comment down here. Crazing, so crazing is probably a little bit similar to plastic cracking, but it's more associated with a thick paste layer on the surface of the concrete. So can occur with wet mixes or overworking of the concrete surface or finishing while the bleed water is present. So again, if you force or work bleed water into the concrete, you're going to increase the water cement ratio at the surface. You'll make that surface paste weaker and more susceptible to cracking. Curing we've spoken about, so there's some references here. We should be trying to cure for a minimum of 3 days, but increase to 7 days if possible. We've spoken about curing methods, and there's a note to be a little bit careful. If you're using decorative or colored concrete, it's possible that damp sand or wet hessian may cause staining. So just need to be a little bit cautious of the curing method if that aesthetic appearance is a key feature. So jointing. So we're talking about different types of joints, so isolation or expansion joints that allow for movement, and then control joints that control where the concrete cracks. And then also construction joints if there's a break in the concrete placement. So there's a good example of a control joint here where they've done the control joint at a fitting. So the fitting beam here is probably making this area a weak point anyway. And if you didn't put the control joint here, there's a good chance it would crack here by itself. So the design has done the right thing and put the control joint there. You can see there's an expansion joint here if the length is greater than 15 meters. And I've seen a video of a footpath which in the heat of the day comes up like this because of expansion of the concrete, and then comes back down again in the evening. So the use of those expansion joints is pretty important. You've got some isolation joints here just to make sure that you're not making this into one rigid structure. You've got a separate structure and you're not keying into it. And a good example here on this control joint, where instead of going right across to this edge in a straight line, you've come to this edge in a perpendicular way. And the reason for doing that is you've avoided making a sharp angle that might cause a point where it might crack. So yeah, really, really important to get this joint detail correct, just to make sure that you get a nice looking product at the end. This is where you've got an isolation joint up to another structure, and you'll notice that there's a note to use a suitable silica or polyurethane sealant here because you don't want the water soaking through and getting through this gap and into this other structure. Now we've spoken about concrete being a porous substance, particularly if it's lower strength, and avoiding these water ingress points is important. And this is just an example where there's a control joint and you've got a bar or a dowel going through it, but you've got a bond breaking compound on one end, so the two pieces can still pull apart a little as they shrink without being held together by this dowel. And there's just some rules here about expansion joints, the frequency, and depending on the thickness of the pavement. So I'm not going to read through all of these CCAA publications. It's just important that you're aware that there are a lot of resources available on the CCAA website. You can access those for free, so no need to be a member or to pay any fees. So there's technical publications including briefings, data sheets, guides, and technical notes. These are some examples of the briefings that are available. These are some of the data sheets. You'll notice there's one here that covers plastic shrinkage cracking. Another one that covers hot weather concreting, which we can't avoid sometimes in Brisbane. And there's also data sheets covering curing and compaction. So it's some pretty good reference material there. These are some of the other data sheets. You'll notice at the top, we've got one on slab edge dampness. So slab edge dampness is basically when water can access concrete, and concrete being a porous substance, it'll go through the concrete and potentially carry salts and show efflorescence, which you sometimes see just on the inside of the garage. And some guides. More guides. And we've got time for questions and answers. So I'll hand control back to Harm. Let me just
Fantastic. Thanks so much, Mike. That was absolutely fantastic. Loads of very, very helpful information there. And we will get into the Q&A in just a second. We've got some great questions that have come through for us as well. And then we'll get into the questions. Okay, super. All right, Mike, I hope you're ready.
Yeah, all ready.
Fantastic. Okay, so we'll go for the first question we've got here. First one is, how do I prevent efflorescence around the edges of house and garage slabs?
Okay, that's a good question. I just touched on that on the last slide, didn't I?
Yes,
So
yes.
So efflorescence is basically salts that water is carrying through the concrete, and as the water travels up, normally through the sides of the concrete, particularly if you're talking, I guess, about a garage, that water is traveling in through the side of the concrete and making its way to the surface, and as it evaporates, it's leaving the salts, which is that efflorescence, that white salty finish. So the best way to avoid it is to stop the water getting into the concrete. So if we turn the vapor barrier up around the base of that concrete, then the water can't get through. If the water can't get through, it can't carry those water and those salts through the concrete. Having said that, if you're in the situation where, for whatever reason, that vapor barrier is not in place, you can mitigate it by ordering higher strength concrete that's less porous. But if it's occurred and you can't get at a vapor phase barrier, if it's been removed, then it's pretty difficult to stop. So it really comes down to just constructing it in the right way to avoid in the first place.
Right, fantastic.
And I should say too that some of the other things we spoke about in terms of compaction and curing, you remember that they have a pretty big impact on reducing porosity of the concrete. So again, it comes down to construction and the way it's constructed, but there are a number of things that can be done to minimize the risk of that slab edge dampness.
Fantastic. That I think answers a lot of similar questions that we've had come through. So that's fantastic. Thank you. We've got another question here. What are the categorization of cracks in concrete?
Yeah, so we covered quite a few different cracks. So we talked about dry and shrinkage cracking, which is just that gradual drying of concrete over, typically over the first 6 to 8 weeks is when most of it occurs. And that's just due to drying and the concrete shrinking as it dries. We spoke about settlement cracking, which is cracking that occurs as the concrete settles and as the bleed water rises and tends to follow the pattern of the steel reinforcing. We spoke about plastic shrinkage cracking, which is what happens when the surface of the concrete dries out while the rest of the concrete is still in the plastic state. And we spoke about concrete that happens because we don't have the right ground support underneath it. But I should point out that there's some really good material available on the CCAA website. So I think we saw when we went through some of those documents that are available that they do cover all those different types of cracking. So yeah, I'd definitely recommend people have a look at what's available on that website.
Perfect, thank you. And this is probably not so much a question as more of a statement that might sort of cover a multitude of different questions we've had come through. So we've received quite a few questions relating to concrete cracking, in particular surface cracking or crazing, plastic or shrinkage cracks, ground preparation, vibration, and the application of curing compounds. I know that a lot of these topics were covered in the presentation and in some of the answers you've provided, but if you wouldn't mind, would you be able to go through again what you see is the best way to help minimize cracking of concrete?
Yeah, sure. That's a good question. So we did cover it during the presentation, but if I was going to summarize what the most important takeaways are, no surprise to anyone, don't add excess water.
It's a big one, yes.
I said at the beginning, if you take away one thing from this, excess water is not good. And look, it's probably the most important thing for avoiding all of these types of cracking, but also you know, proper compaction and curing also play a really big role. And just being aware of the environmental conditions and taking precautions if it's really hot and dry. So you know, don't add excess water, do compact, do cure, do take precautions against harsh environmental conditions. They're probably the main takeaways I would suggest you come away with. And if you want to, you know, really get into a bit more research and a bit of a deeper understanding, then yeah, those documents are available on the CCAA website.
Great, thank you. What have we got? Another question here. What do you see as the 3 most common defects in concrete and why?
Yeah, okay. So cracking probably
Mm.
is one of the top 3.
Yes.
And you know, for all the reasons that we've already covered, just people not compacting, not curing, adding excess water, not taking precautions in hot, dry conditions, all of those things lead to cracking. Finishing, so you know, leaving that finishing too late and not getting a nice smooth finish, not getting a nice dense finish, finishing in the wrong way and leaving a horrible dusty finish, and that's also from, you know, finishing too early and working bleed water into the concrete, or you know, the rain comes and you don't keep the rain off and you just work that rainwater into the concrete. So that you know, that finishing of the concrete, and particularly that dusty or rough surface is probably a fairly common occurrence. And then again, you know, absorption of water into the concrete after it's set, and seeing that patchy efflorescence because you haven't got the vapor barrier where you should have, or the concrete's very porous. So yeah, they're probably the top 3: the cracking, finishing related issues, and moisture related issues.
That's fantastic. Thank you once again. Oh, sorry, were you about to? put in
I,
another
I,
comment there.
I did just recall a time I went to look at a slab edge dampness issue, and it was on Bribie Island, so quite a saline environment. And we found that we had a lot of problems on the south side of the house. And the reason being was that the water just wasn't getting away, and also the vapor phase barrier wasn't turned up against the edge of the slab. And when we put a hose into the drain pipe, there was a problem with the drainage as well. That water just wasn't getting away to the side of the street as it should have. So that's sort of other reasons why you can get slab edge dampness issues as well. Just poor drainage, water not getting away from the sides of the house, typically on the shady side of the house where it's not getting the sun as well.
Gotcha. What have we got here? We've got a couple of questions relating to driveways as well, so we've probably got time for maybe 2 more questions.
Yep.
So we've got the first question here. Do you still provide control joints in an exposed driveway slab?
Yeah, absolutely. I mean, whether it's normal concrete or exposed or decorative concrete, it still shrinks in the same way. So you do need to do that proper joint design. Particularly, people order that decorative concrete as for the aesthetic look, and the last thing they want are unsightly, uncontrolled cracks. So yeah, the same applies, especially applies, I would say, for decorative concrete.
Perfect, thank you. Where else? Okay, so for driveways, another question regarding driveways, and we've got, when do the control joints need to be cut in after the pour?
Yes, so if you're using saw cuts, ideally the same day, or at the very latest early the next day, and that probably varies a little bit depending on the season. Obviously, if it's really hot, you're not going to have as much time, and if it's in the middle of winter, you'll have a little more time. So you need to do it as early as possible, so you avoid you avoid cracks appearing where they want to, but
Yes.
not too early, so you get a rough cut. So you kind of got to use a little bit of experience there and take into account what the weather's like and what season we're in.
Perfect. Okay, now we've probably got time for maybe 1 more question. Let's see. Here's one. Why aren't moisture barriers mandatory under driveways?
Okay, it's a good question. So look, it's not mandatory, but you certainly can undertake measures to avoid some of the problems of not using plastic. And one of those things I referred to in the presentation earlier is just wetting down that base, not so that there's puddles, but just making sure that that base is moist, so the ground's not going to suck the water out of the concrete, and the water is available in the concrete to come up as bleed water and help prevent the risk of plastic cracking, and sort of give you the result that you're after. So that's one precaution that you can take if you're not using plastic.
That's great. Thank you, Mike. And I've got 2 more questions if you've got some time to spend.
Yep.
Okay, so what have we got here? The question is, I am concreting an area that is surrounded on 3 sides by concrete. Should I put an expansion joint, and in brackets spongy stuff, on all 3 sides?
Yeah, so certainly if it's a separate structure, it's a good idea to isolate it. Once you start locking in one element with another, if it's not specifically designed to be locked together, there's a real risk that you're going to put stresses and forces on that existing structure or on the new structure that's going to lead to cracks where you don't want them. So isolating those 2 separate structures, unless they're designed to be a single structure, is certainly the way to go, I would think.
Perfect, thank you. And I think this is probably be the last question that we can get to. We've got, where are we? Question, okay, so do curing times vary with temperature and thickness?
Yeah, so generally, if you look at AS 3600, they vary with the strength and the exposure class. So AS 3600 outlines what exposure class you need under certain conditions. So it makes a distinction between acid sulfate soils or other aggressive conditions like dairy farms, for example, where you might have milk and urine which contain acid, or coastal locations where you've got chlorides, and generally where the durability concerns are higher, you use higher strength concrete. And we understand that, right? Because when you use higher strength concrete, your water cement ratio is lower, more of the water is taken up to hydrate the cement, and there's less pores left in the concrete when any excess water evaporates. So yeah, generally when it comes to curing time, and specifically in AS 3600, it depends on the exposure class or the strength. So they're saying where your exposure class is higher, your strength needs to be higher, and your curing regime needs to be better.
That's fantastic, Mike. Thank you so much. We've probably unfortunately come to the end of our presentation for today. So I'd just like to, on behalf of the QBCC, thank you, Mike, for being our presenter for the face-to-face sessions and also for this webinar. And thank you to the CCAA for their participation in tonight's webinar as well. Also, thank you to everyone involved in the tradie tour. And we'd like to thank you for your attendance. One last thing, remember to complete the short survey after this event that seeks your feedback. And thank you, folks, and bye for now.
Thanks, Sam.
Thank you.